So this is the second of the morning lectures of day 2. So what we're going to do now is we're going to shift gears to error correction, error detection. So we talked about how you transmit a message. And we saw ways to do it efficiently. We saw ways to encrypt it. So hopefully only the intended recipient can read it. The problem is, what if they don't receive the message you meant to send? So there's a lot of great examples about how punctuation can kill. If you don't punctuate correctly, you can. So the most famous is koala eats, shoots, and leaves. So what if there's a mistransmission? So we're going to send zeros and ones and say probability P receive correct. All right. So we're just talking about, so we're sending strings of zeros and ones, and we want to know what is the probability, we'll call it P, that we send a 0 and the person receives a 0, we send a 1 and they receive 1. I'll assume it's the same probability for each. What should P be very close to? 1. Ideally. If P is not close to 1, then there's going to be a lot of transmission errors. There's another value that P could be close to, and you'd be fine. 0. And I've talked about the wonderful Seinfeld episode where George Costanza realizes that every decision he's made in his life is wrong. And he goes up to an attractive woman at the restaurant and says, my name is George, I'm unemployed and I live with my parents. Hi! And then he eventually gets an interview with the New York Yankees and lands a job after insulting Steinbrenner. Most things in life aren't binary. So most things in life, if you know one wrong answer, that's not enough to get the right answer. But this is an advantage of base 2. So we want P close to 0. Well, if it's close to 0, just look at 1 minus P. So we'll assume P is very close to 1, so that it's unlikely to make an error. So if it's unlikely to make an error, it's really unlikely to make 2 errors, unless you have a huge stream of digits. So most of the time, you can assume almost all the digits are correct. Maybe 1 is wrong. And so the first problem is error detection. Can you tell if a mistake was made? Then the next thing is, can you fix the mistake? So the story that's often told is how George Hamming was working, I think, at Bell Labs, and he was low person on the totem pole. So he got his punch cards in, but they would only run his stuff on the weekend. And he'd come back on Monday, and they'd tell him, okay, everything ran up to line 14 when the computer stopped. So he'd fix it, and then the next week, okay, now we're into line 16, or 61 or whatever, and then it stopped. And in the exasperation, you go, if the computer can tell that there's a mistake, why can't it just fix the mistake? So can you teach the computer to not only notice that something is wrong, but fix it? If you think about this, for a lot of things, we don't really need good error detection, error correction. We just need good error detection. We can redo something without too much trouble. I think one of the greatest inventions of the 20th century is the scanner that you would see at a supermarket or at a store. Not only does it give you the price, but it also automatically updates the store's inventory. It can look at correlations. It's wonderful. Is it? I'm not sure.
I remember seeing one in the 80s.
Well,
actually, when I worked
but that's on the mainland. I know they existed in Hawaii in, I think, like the 1850s. So my wife and I went there for our honeymoon, and there was and there was a plantation. They had a bunch of vintage food items which had USB barcodes. I had a little conversation with the historian in residence. So if you're in a supermarket and it doesn't scan correctly, it's not that hard to scan it again. So in something like that, you don't have to be able to correct the error. You just have to know it's scanned incorrectly, and then you can try again. The cost is very low.
the actual scan.
The actual scan, right. If you're transmitting a huge file, and it takes a while to download the whole file, you don't want to download the whole thing, realize there was a mistake, and then have to retransmit the whole thing. You want to be detecting and correcting errors as you go along. So the first thing is, can you detect an error? So we want to send 100111101. Let's say we want to send that message. How might we send it so that somebody could tell if an error was made? So again, we will assume that it's unlikely but possible to make one error, but extremely unlikely to make two errors. So one thing is to send it twice. So you could send, and then we just send it again. 100111101. So that's what. So it's just tell me twice. There's another way you could tell me twice. There's another way you could tell me twice.
Compare the inverse.
No, I wouldn't do the inverse, but I mean, you could do the inverse, but why?
It would be kind of like, I think the end result would be pretty similar to tell me twice.
It would be extremely similar to tell me twice.
Sort of thing, yeah.
But how else could we arrange the digits?
In reverse. Oh, count them. Count the ones and count the zeros?
No, because we.
Sum them?
So counting would actually work. Summing would work. But I'm saying here I wrote the message and then I wrote the message again.
Yeah.
How else could we do it? I still want to tell you twice. We can check the digit, but
Are we just looking to see if the transmission was sent correctly? We're not trying to fix the error yet?
okay, so you're close.
What? I was going to say.
Well, I don't want to add. I want to send the message twice, but here I sent the message and then I sent the message again.
Could you send it 110?
Yes, I could send 1 1 0 0 0 0 1 1 1 1 1 1 0 0 1 1. And if I send it like this, as you're transmitting, I can immediately tell when an error was made or when something was correct. Whereas here, I have to wait until the whole message is sent before I start making those comparisons.
That doesn't solve the question, though, of which one is the correct digit, though.
It doesn't.
Right.
So this,
Right.
so you're jumping ahead. Excellent.
So you're assuming that the error is that something got left out.
Right. So if we receive, say we receive 110001 1111110111. We look at things in blocks of 2. And if we look at things in blocks of 2, there are 2 blocks that we are suspicious of. And in fact, we know this has to be wrong, and we know this has to be wrong. We don't know what's right.
Why sorry?
Because they're not the same. Because we're transmitting each digit twice, if we receive 01 and 01, we know we made a mistake.
Each pairing should be identical.
Each pairing should be identical. So you can only receive
2 ones or 2 zeros.
Okay, that's what it said.
right?
Yeah, I thought it had to do with the colors.
Yep, nope. So we don't know if 11 is correct. It's possible we made 2 errors and meant to send 00. But because the probability of an error is so small, we can be reasonably confident that if we get 11, 1 was meant.
Since the message is being transmitted really only in one time, though, you need some sort of way to make sure that it wasn't being truncated at the end, too, though. Right?
What do you mean?
Well, so for example, let's just say there's a transmission error,
Right.
and the last 2 digits just don't make it.
Oh, okay.
You still need some sort of way to know that you've reached the end.
Correct. So you would want to know what the length is.
Right.
Yes. So if, but then that would be a failure of 2. And so you're right that there are issues if you could lose digits. And you could lose a digit in the middle, for instance, and then you would know that there'd be a problem. Or you could, if you lose 2 digits, hopefully you would get a whole slew of errors and realize something must be wrong.
Yeah, but in the first method, that is taken care of, right? Because in the first method, it's hard to imagine something like the message getting truncated twice in the exact same spot.
Right.
So that.
But then you would have large numbers of, right, so.
It's just an advantage negative. Sort
Yes.
of thing, yeah.
So somebody had already mentioned how you can make tell me twice better.
You do it 3 times.
You do it 3 times.
Whichever one came up 2 times, you can be reasonably sure.
Right.
it's
What a million.
So the more times you do it, so instead of tell me twice, tell me thrice. Exactly. What comes after thrice? I don't know. Is there a There's no good word for beyond thrice?
I think it's twice. I bumped that up once.
How about twice?
Or double twice? So you would send 111 for 1, and you would send 000 for 0. And any other message means an error. So if you think about it, you can write 111 here, you can write 000 down here. And then over here I would have the errors 110, 101, 011. Over here I would have 0.
Yeah.
It is the hat problem. And then the last one would be 100. So we want to consider all 8 messages. So what we're going to do here is we're going to have a distance metric. I'm splitting the set of 8 messages into 2 sets. So we have 8 triples that we can send. From 000 to 111. And we want to talk about how far apart are 2 messages. So the distance between 2 messages is equal to the number of different digits. So how far apart are 111 and 000? They're 3 apart. So the distance from 111 to 000 is 3. What's the distance from 111 to 110? And the distance from 000 to 110? 2. So these messages here are all 1 unit from 111. These messages here are all 1 unit from 000. So if you receive anything in blue, you know a mistake was made. If you receive one of the blacks, it's possible a mistake was made, but you would have had to transmit 3 incorrect digits. Unlikely. So if I make one of these, it's far more likely that 111 was meant than 000 was meant. The probability of being here is
Because the distance is small.
small, right? So if you receive 111, you would correct to 111. So this is a tell me 3 times. Majority rules is another way to phrase it. This is often used in the military in targeting solutions. When you want to figure out where to fire, if 2 out of 3 computers agree, you're probably good enough. Right?
Manuscript tradition.
I'm sorry?
Ancient manuscript tradition. You have, manuscript of Virgil.
Right.
And there's, some scribe made this mistake, but then the other 2 had something else.
Right.
Interesting little side note, my father-in-law was an artilleryman in Vietnam, and he said that, they used to do the calculations by hand, and when they got a computer, they were ordered to use it. And he said that if they had a disagreement with the computer, they went with their manual calculations. They didn't trust it.
Really?
Yeah. But I mean, this is the...
Yeah, well, it also depends on
Yeah.
on which computers you're using and who you trust. Well, the thing is, are you more likely to type something wrong into a computer than to do something wrong on the paper when you're more familiar with the paper? Yeah. So this is an absolutely wonderful approach. And we're going to talk a lot about the advantages and disadvantages. So one of the advantages is that it can correct an error. So not only does it say you were wrong, but here's what you meant. But at what cost? How expensive is this? So you need to come up with a good metric. So cost-benefit analysis. So for instance, yes. So 1/3 of your message is data. Only 1/3 is data. So this means a majority of your message is redundant check. So I won't go into details, but there was a car company that noticed that one of their parts was not failing with a high enough frequency. There was a car company that noticed that one of their parts was not failing with a high enough frequency.
Was it failing?
Was not failing with a high enough frequency. They were making it too well.
Oh.
And it was
Too much money, yeah.
Right. So for instance, imagine you can have a process that will be 99.99999% accurate for $10 million, or a process that will be 99.9999% accurate for $1,000. Is it worth spending all that extra money on a small incremental improvement there?
Absolutely. We're Americans.
Well, but given that you only have a finite amount of money, you would probably want to shift some of that to another part of the car that's failing at a higher frequency.
Oh yeah.
So when you only have finite resources, if something is not failing at a high enough frequency, you are potentially over-engineering that and spending too much resources on that.
I mean, I don't know, that seems like a very cynical way to go about mechanical engineering, but I'm assuming this was a car company in the 70s, so that probably makes sense.
It makes perfect sense. It's all about how you sell it to the public.
They make their money on replacement parts, right? So it's.
Well, for some things, yes. But if you have too many replacements, people will then go to another company.
That's why your cell phone dies after 2 years, right? When the warranty runs out.
I don't know, I think
They time it very well.
Mechanically, you can definitely engineer things to not fail, and it doesn't necessarily mean that you're going to have to spend a lot of time.
Correct, but there are some things where, with a lot of additional resources, you can make it infinitesimally better, and it's just not the best use of your resources.
Yeah, there's a point
So
where you...
there's a point. So here, the problem is 1/3 of our message is the data we want to send, and 2/3 is redundancy.
Right.
But you imagine you are captain of a nuclear sub.
Yeah.
You surface, you get the message, and then you come down. It's extremely important that you get the right message because it's hard for you to keep surfacing.
That's costly.
That's costly. But being surfaced and waiting for the message is costly as well.
Right.
So we want to do better than 1/3.
You don't want to go back up and down many times.
So what grade would you give this?
Say that one more time.
What grade would you give 1/3 of your... Would you give them an A, a B, a C, a D, an F? A B?
D.
I mean, it's really interesting. I mean, a majority of your message is redundancy, but you're able to transmit the message and people can correct errors.
I would say it's B plus work. Great.
What could you do to be more convinced that your answer is correct? I'm sorry? Keep going. Tell me 4 times. Tell me 5 times. And then the more times you do it, the more confident you are that the message is correct. So we agreed that if the probability of failure is low, I don't want to transmit things 4 times and 5 times.
But isn't 4 wouldn't even be as efficient because you wouldn't have the majority anymore?
Well, with 4 you would have a problem if there was a split.
But any odd number would work.
So 5 would work better, but with 4, you are right that you wouldn't necessarily know how to correct. So as was remarked, this is very similar to the hat problem. So we had 3 people, and we put hats on them, and the hats can be either white or black. And each person has a 50-50 chance of getting a white hat or getting a black hat. And the rule was, if everybody who speaks is correct, everybody gets $1 million. If even one person who speaks is wrong, everybody is killed. What's the best strategy? You can do 50% by having one person always say white or black, doesn't matter. And then the other 2 people are always silent. So you can easily do 50%. No, 6 out of 6 out of. So how do you get 6 out of 8?
Well, there's 6 different ways where one person has a unique color.
Good. So we have white, 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 black, white, black, black. I'm sorry. I'm sorry. Yeah, that's it. White, black, white, black, white, white, and then so on and so on, going all the way down. And then what you do is person 1, 2, and 3. The rule is if you see 2 hats of the same color, you guess the opposite. So in this case, you would be wrong, wrong, and wrong. In this case, only one person sees 2 hats of the same color. So only person 3 speaks and they're correct. In this case, only person 2 speaks and they're correct. In this case, only person 1 speaks and they're correct. And then same with the other ones. So notice, when person 3 speaks, person 3 is right only half the time. Should you be able to do better than being right half the time? As an individual when you speak. No, your hat is put on randomly. You should not be able to do better than half the time.
But as a group, they do well.
So when you feel, boy, do you feel. You pile up all your wrong answers together and you spread your right answers as far apart as you can. So there's a lot of problems like this where you want to concentrate your failure. And by doing this, you actually write 3 out of 4 or 6 out of 8 times. So you could actually have a 75% success rate.
If you look and the other two people have different colors here, you pass. Is that what
You
you're
shouldn't
saying?
say anything.
You pass.
Right, you would just be
Oh,
silent.
I might be helpful if we wrote down
So another.
Right, so
they would come up with some sort of algorithm.
if C,
Right, yeah.
same color on both, say opposite,
Right, that's the best choice there.
else you're silent.
There you go.
And so
That's the plan they come up with.
that's the plan they come up with, and you'll be right 3 out of 4 times.
That's the logic statement there.
So the idea here is to really concentrate your failures. Because you can't have anybody doing better than right half the time. So I'm going to give you a fun problem that I had when probably I was in high school taking math competitions. And it's somewhat related to this. So it's one of these problems where you have jelly beans and 2 different jars. So in this version, you have a prisoner. They have 50 red jelly beans and 50 blue jelly beans. And you have 2 jars. And you can divide the jelly beans however you want among the 2 jars. And then you will randomly choose a jar, you're blindfolded, and you'll randomly pull out a jelly bean. And if you get a red jelly bean, you are pardoned and you get to go free. And if you get a blue jelly bean, you're killed. Or you go back to jail, depending on how you want to do it. So the question is, how do you maximize your chance of surviving? So first of all, can somebody give me something that will work 50% times? So you have 50 red, 50 blue, 2 jars.
And both are mixed?
You get to choose.
You
Split.
Yeah.
Okay, so what do you do?
Put them exactly
Put all the reds on
as they
the
are.
So put all the reds in one?
Yeah.
Okay, so put 50 reds here. And what do I do here? 50 blue. And my chance of surviving now is 50%. Right? Choose
I'm randomly picking one of the others.
jar at random. Choose bean at random. Win at red.
Can you put them all in jars and you have to put a jelly bean in each jar?
You don't have to put a jelly bean in each jar, but if one jar
Zero.
is empty,
Then
then you can't survive.
Right.
So,
So you have to choose the right jar on that.
right. So this one will give you a 50% chance of living. Can anybody give me another way to have a 50% chance of winning?
Half and each.
Yeah, so we could do 25 red, 25 blue, 25 red, 25 blue. That will also be 50%. Can you do better than 50%? I'm sorry? For sure, right? Otherwise, I probably wouldn't be talking about this right after a previous problem where we did better than 50%. You only get one pick.
We put 1 red in 1 jar.
So you put 1 red in 1 jar.
99 in the other.
And then here, you have 50 blue and 1 red.
49.
49 red. And this is the best you can do.
Oh, because when you pick one of the jars, you're automatically getting a red.
Right.
And the others all should.
So it's close to 3/4. So when I taught this with probability, my students had calculus, so we could analyze it with calculus. But one of my students wanted to know, can you solve this without calculus? And you can actually prove that this is the best you can do without calculus, as follows. So one possibility is, of course, just to have a computer go through every possible case and see that this is best. But if I replace 50 with 10 to the 50, your computer can't do that. So how do we prove this is the best? So we have 2 jars. We have some number of red here and some number of blue here. And then we have 50 minus R here and 50 minus B here. Do we agree that it's not possible that both jars could give us less than a 50% chance of surviving? At least one of the jars has to have either more reds than the other or the same number of reds. So one of the jars is at least 50%. Right? And then if this jar is at least 50%, this one is at most 50%. Okay, well, if this was 50%, then this would have to be 50% as well. And that would give us a 50% total. So I can ignore the case where it's at least, but I can say it exceeds 50%. So I'll have one jar that's more than 50% and one jar that's less than. What is the best you could have for more than 50%? The best you could do is 100%. What is the best you could do that's less than 50%? 50% is not less than 50%.
Well, 49 points, yeah.
Give it to me as a fraction.
Oh, God.
49 out of what? Out of 99. Right? That's the closest fraction to 50% that we can get. Right? If the denominator was 100, well, then we're in trouble, because if we have 100 there, we would have to be 49 out of 100 here, and then the other one clearly won't work. So the best fraction we can do is 49 out of 99. And so now we know that this has to be the best. It's actually possible that there could be another arrangement that does equally well. There isn't. But this at least proves that you can't do better than this. So, ideally putting one red here and everything else here. The other thing you could do is you could assume you have some blues here, but fewer blues than reds, and show that the probability is increasing as you move the blues over to the other one. And then once it has some number of reds, it's actually better if you move all the reds over. So you could walk like that to get to, that if you had anything that you thought was better, you could flow and eventually get that this has to be the best. But this is the idea of, when you lose, concentrate your losses, and when you win, just barely squeak by. It's the same as the hat problem. We want to just barely make it in this case and give us as much freedom as possible to put in there. All right, so this is related to the hats problem, and that's related to the tell me 3 times. But we have issues with the tell me 3 times. A lot of the message is devoted to data checking, and that's terrible. So we want to have a more efficient way to transmit information. So I don't want to have a majority of my message being redundancy. So what do you think is a bare minimum that would be acceptable?
Oh, what do you mean by that exactly?
Well, so right now we had 1/3 of the message was our data and 2/3 was redundancy.
Right.
What's the bare minimum that you would consider acceptable?
In terms of redundancy?
Yeah.
I think 2/3 is pretty good.
So if you like 1/3, then we don't have to develop any more mathematics.
Under baseball.
So you can wait a long. So when the message is slow like that, this goes back to like 10 years ago with the streaming video that was. So you really want to. What do you think is a minimum acceptable requirement for what percent of your message should be the data you want to send?
50%.
You should be at least 50%, or maybe even slightly, at least 50% or over 50%. I want at least half or majority of my message to actually be the data I care about. I should be spending more time transmitting. So there's lots of different schemes you can do. So the first one I want to talk about is the checked digit scheme. And there's lots of ways of doing this. And you can sometimes see this with barcodes and whatnot. This is for situations where all you want to do is detect an error. So this is just detection. It does not fix things. And the way it works is, let's say we have a string of digits, 0, 1, 1, 0, 1, 1, 1, 0, 1. Then you add one extra digit at the end. And 1, 2, 3, 4, 6, 7.
Oh, I was wondering what that was.
Yes. So this is 1 if some is odd, and it's 0 if sum is even. So I look at this over here. And by saying the sum is odd, it means I have an odd number of ones. Or saying it's even, I have an even number of ones. So here I have 1, 2, 3, 4, 5, I have 7 ones, so the check digit should be a 1. So imagine I receive the following message. 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0. Or I receive 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1. I know both of these messages have to be wrong. Because here I've got 1, 2, 3, 4, 5, 6, 7. And to the check digit should be a 1, it's a 0. So this means a mistake was made. I don't know if the mistake was I transmitted the check digit wrong or I transmitted something in the message wrong. So over here I have 1, 2, 3, 4, 5, 6. This should be a 0. So there's a mistake. And here, the check digit was transmitted correctly. The error was over here.
So as long as there aren't two mistakes, right?
So, and so, yes.
The assumption is that the mistake is going to be that a number is left out or added in rather than a 0 is transmitted as a 1. But that, is that
No, that's the mistake that this catches. It catches 0 becomes a 1 or 1 becomes a 0. That's what it checks.
Not the sum of the digits, but the sum of the...
Well, if you look at the sum of the digits, that's the same as the number of ones.
No, what I mean is like there are 1, 2, 3, 4, 5, 6, 7, 8. I'm adding up...
1 plus 0 plus 1 plus 1 plus 0 plus 1 plus 1 plus 1 plus 0 plus 1.
I'm not doing that. I'm doing
Okay.
I'm counting how many digits are in the string.
Telling how long the string is.
No, it's not the length of the string. It's the sum is the sum of the digits.
I understand.
So the digit sum. So it's the same as, do we have an odd or an even number of ones? If we have an even number of ones, the check digit is 0. If we have an odd number of ones, the check digit is 1. The problem is it only catches certain types of mistakes. It catches a 0 being sent as a 1 or 1 being sent as a 0. If I were to send the following, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 7 and 1, yes. So it works. What I did is I transposed 2 digits. I flipped these 2 digits. And if you flip the order of 2 digits, the check digit scheme is not able to catch something like that.
Well,
Was
unless
it the previous
unless-
2? Oh, sorry.
And isn't that like making the two mistakes that we,
Kind of. I mean, the
Yes.
likelihood of that being very low.
that's a two mistake.
And in the world of the UPC,
Well, so it depends. So if you've ever typed on a computer or a typewriter, depending on how fast you're typing, you do sometimes transpose 2 letters. So transposing 2 letters when you type is not an uncommon mistake.
And it's one
It's
mistake.
considered one mistake.
So it's considered one mistake, but it's a transposition mistake.
Yeah.
And so really, yes, it's 2 mistakes. That's wrong and that's wrong. Or you can view it as a transpositional mistake.
The method of casting out 9s to check.
So there's more involved schemes that you can use using base 10 or base 11. And there's actually ways to have it so that you can tell not only if a digit was transmitted wrong, but if 2 digits were transposed. So there's whole schemes of these, and these are all very elementary at the same level of this. It's just basically middle school algebra. It's just looking at these check digit stuff. The more involved system you have, the more you can do. And these aren't that bad, especially for computers to handle. Checking the number of ones, the parity, is it even, is it odd, that's not so bad. But if you want to start detecting transpositions, then you just need a more involved test.
I would imagine the transposition error would be more likely to happen, though, as the message was originally being created rather than transmitted.
Well, it depends how the message is being transmitted.
I suppose that's true. I mean, if we're talking about electronically, though, I don't know. I mean, do computers make transposition errors very often? That seems more like a human.
To me, a transposition is more of a human error.
Yeah.
So if you have a barcode scanner, it's not bad to just scan it again if it doesn't work. And hopefully they will notice, if you're scanning in I don't know, the mini fudge brownies, which in my family we just cross out the word brownies and write muffins so that it can count as breakfast. If you scan that in, and it now comes in as a, you know,
Banana.
I was going to say as a dinette set that the store is selling, you know, where the price is now several $100s. You would hope the person at the register or when you're looking at the receipt, you would notice, huh,
Doesn't look right.
doesn't look right.
Error detection.
Right. But it is possible that when you scan it, it could get another valid code. So one thing is you want to make sure that no things are within one of each other.
I was gonna say, that's one of the reasons why they don't assign like products, similar
Yes.
barcodes, yeah.
Yep. And so you want to have things spread out so that it's quite clear that, okay, I don't think you were buying a dinette set.
It's kind of like what you've been saying though, like the idea is that you take your failures
Yes.
and really maximize them. So if you're off, you're not off by a few cents. You're
Correct.
off by
You're-
hundreds of dollars.
Exactly. And so you should be able to realize. Now,
Someone actually thought of the fact that barcodes shouldn't be similar for similar items.
Yeah,
oh yeah.
totally see this.
Now, of course, you could be trying to buy a dinette set and be charged for some fudge muffins.
Yeah, they noticed that too. I tried that.
I wish I could remember. I'll have to rederive some of these effluents. So, some of the lectures are extremely well prepared, and I thought about them intensely in the week between when we met. Other parts are just on the spot. What do you seem to be interested in? And I'm hoping I'm going in the right direction. So, along the lines of how complicated rules are, let's just digress into divisibility rules, because I actually learned a new rule this year that I did not know. So some divisibility rules are so easy I'm not even going to bother doing much on them. What's the easiest divisibility rule? Okay, 2, are the last 2 digits, the last digit, even. 4 isn't so bad, you look at the last 2 digits. 8 isn't so bad, you look at the last 3 digits. 5 isn't so bad. 11 is fun. 3 and 9 are nice. Who does not know the rule for 3? The sum of the digits. I'm sorry? I'm sorry?
A rule that how that, something is divisible by a certain number. You know what I'm saying?
Oh, okay.
Right. So it's divisible by 5 if it ends with a 5 or a 0.
I understand. Thank you.
So if I give you a number like 314, I'm going to do proof by example, which we know it doesn't exist, but I can write this as 3 times 100 plus 1 times 10 plus 4 times 1. I can write 100 as 99 plus 1. I can write 10 as 9 plus 1. A little bit. But what I'm going to do now is this is 3 times 99 plus 1 times 9. And over here it's going to be 3 plus 4 plus 1. So this, each of these numbers is a multiple of 3. So 3 always divides this. So if 3 divides this sum, then 3 has to divide the original number. Conversely, if 3 divides the original number, then 3 must divide this sum. So the
You just proved the divisibility rule for 3.
right. Now I should, instead of doing 3, 1, 4, I should do A1, A2, A3. But I wrote it like this because now we also have the divisibility rule for 9. Because this number here is a multiple of 9. So 11 is what's remarked as fun. So do you remember the rule for 11?
Yeah, so you look at the powers of 10, either one above or one below a multiple of 11.
So 10 is 11 minus 1. 100 is 99 plus 1, which is 9 times 11 plus 1. 1,000 is 10 times 100. Well, if you now multiply things out, you're going to get multiple of 11, multiple of 11, multiple of 11, negative 1. So this is just negative 1 mod 11.
1,001 is...
So 10,000 would just be 1 mod 11, so it alternates. So if I give you a number like, 6, 7, 8, 5, I look at 6 minus 7 plus 8 minus 5. I look at the alternating sum.
What? I don't know why you did that.
Okay, so
Off the left. I don't know why you did 6
so we have 6 times 1,000 plus 7 times
Thank you. Yeah.
100, right?
Yeah, I would think
Plus-
of that as minus 6 to begin with.
Yeah, so if you want to do it correctly. So now 1,000 is going to be negative 1, so it would be negative 6 plus 7 minus 8 plus 5 mod 11. And so when you add that, this gives you a +1, and this gives you a -3, so it's not 0.
So therefore it's not.
It's not divisible by 11.
Cool.
So what should I change the 5 to make it a multiple?
2 higher. Right?
So this is a +1, so I need a -1. So if I make this a 7, and now we get 0. And so this is the rule for divisibility by 11. So we've got 2, 4, 8, 5, 3, 9. So what I would say is look at the alternating sum of digits. If the alternating sum of digits is a multiple of 11, your number is a multiple of 11. So if alternating sum of digits is a multiple of 11, so technically we should start off with a minus sign, but it doesn't really matter if I start off with a minus sign or a plus sign. It's only going to change things. Now what's really nice about this is, imagine I give you a monster number. 3, 8, 9, 7, 2, 4, 3, 2. 6. I don't know. Let's make this a 9. Let's make this a 1. So is this a multiple of 11? All right, so I could look at 3, maybe 3 minus 3 plus 8. Let's make this 9 and 1. -1 plus 7 minus 2 plus 4 minus 3 plus 9 minus 1. All right. So 8 and 7 is 15, plus 4 is 19, plus 28. And then I got a -3, -4, -5, -6, -7, -9, -10. And so what do we get? Well, 18 is a really big number. So let's figure out if 18 is a multiple of 11. 1 minus 8 is -7. And it's not. Right. So if you have a really big number, you can just apply this again and again and again. And again, when you apply it even the first time, it's unlikely your number is going to be too extreme.
And that's the same with the rule for 9, right?
Same for the rule of 9.
Digits, you get a multiple of 9. If you don't know it's a multiple of 9, you add up all the digits, you get a multiple
Exactly.
of 9.
And in fact, with the rule of 9 and 3, it's more likely that it's useful to keep applying this, because with 11 with alternating, it's unlikely we're going to get a huge number.
Right.
I tried to stack this by making the second digits larger. But if I take, but if we took, say, 6, 4, 3, 1, 8, 2, 7, 7, 3. So if we wanted to see, is this a multiple of 3? 6 plus 4 is 10, 13, 14, 22, 24, 31, 38, 41. And then we could just do that again and get 5. The other thing you could do is, why add any of these numbers that are multiples of 3? And you could even say, well, look, the 4 and the 2 cancel out like this, the 8 and the 1 cancel out, and I'm just left with, because we don't care about the intermediate steps. The whole goal is, at the end of the day, is my number multiple of 3. I don't care how I get there. The stuff over here is meant to help. So we're almost at lunchtime, so I will end with a challenge, which I will have to rederive. There is a rule for 7.
I know the rule for 7.
Oh, you know the rule for 7?
Yeah.
What is, yes, what is your rule of 7?
The rule, I don't know if it works for big numbers, but you...
Whoa. I feel like Ghostbusters. Nice shooting tag. It's not a rule.
I don't know the rule, I assume it works for big numbers, I just have never applied it to big numbers.
You don't have proof, is what you mean.
It's,
Wait.
Here we go.
So be careful.
Well, why would I have read about this rule if it didn't work? I'm just saying I've never myself applied it before.
I don't think she's ahead.
We separate the last digit.
Okay, so let's say we have, 3, 1, 4, 7.
Take off the last digit.
Yes.
You double it. You subtract
Okay, so,
Well, I show you with 343.
Oh, I
Okay.
can see why you're saying that. You're saying that doesn't, you don't know if that helps with large numbers.
Yeah,
You have to do it
no.
recursively.
Well,
Yeah.
Just have you.
Right, I'm just saying it, just to show you, 7 cubed is 343. Take off the 3, double
well,
it.
let's take 21,987.
Yeah,
Which
just
is
a
3,141 times 7. That's not a real multiple of 7. So we would now get 2198 and 14. So 2198 minus 14 is going to be 2184.
And then you can do that.
218, take away.
Wait. We can just divide this by 7.
Well, you could. But I mean, we're
So if I
just
multiply,
imagining-
well, I know, but I'm saying 7 times 3 is 21. 7 goes to 18.
I'm hoping to avoid long division.
That's the one thing I know.
Dividing by the numbers.
I know one division.
He's just skipping the recursion. So yeah.
Wait, you could do, well, because I'm saying, given that we don't know if the algorithm is correct, I don't want to keep using the algorithm.
Exactly.
Right.
And so the number 2184 is correct. So this is correct for the rule of 7.
We take back our O.
All right. So what we will do is we will still have an hour for lunch. It makes absolutely no sense
Okay,
to.
I just want to comment on that.
Yes.
100 is 2 more than 98, which is multiple of 7.
Mhm.
So when you look at that 7, when you put 14 underneath, you're saying you're 14, no.
Okay.
Yeah,
Why,
how do you
why?
In other words, looking at the
Right.
rest of the number, no.
Okay. So it makes no sense to stop for lunch now and then come back and prove the rule of 7. So let's prove it now, and then we will break for lunch, and it will be an hour break for lunch. It will be an hour break for lunch, okay? Okay?
An hour is way more, I don't know if you're all.
Yeah.
An hour is way more than we have for lunch on a regular day.
Right. And there will be Girl Scout cookies after lunch for people who are looking
I
for
actually
this.
have to meet somebody, but I kind of want to say about, can you approximate, is this like 5,
It should be about a 5-minute.
more, around 5 minutes? Okay.
5 minutes. All right. So here's the rule of 7. So we have our number an minus 1, an minus 2, a2. These are my digits. Well, I'll use D for digits. These are my digits. So maybe you'll think,
Of my n digit.
right, so maybe think I have, 3, 1, 4, 8, something like that. And so this would be D4, D3, D2,
N is the
D1.
number.
Okay.
Okay.
So it's an n digit number.
I'm sorry?
We don't start counting at 0.
So I thought people might be upset if I counted at 0. I'm happy to go all the way down to 0 for for the units digit.
We can't have 0 digits.
Power. I don't know.
Oh, right.
Well, this is 10 to the 0, so your number would be, dn times 10 to the n plus dn minus 1 times 10 to the n minus 1 plus d0 times 10 to the 0. All right, so what are we doing? So we are taking this block here. So our number, let's call our number x, because that's what we like to do as mathematicians. So x is going to be 10 times the number, dn minus 1, d2, d1. So I hope you understand I don't mean the multiplication of these, I just mean this number. So I'll put some kind of strange box around that to just mean that's the number, plus d0.
Okay.
And I want to see if this is a multiple of 7. Okay? 10 is 7 plus 3. Right? So this is the same as 3 times my number. Plus d0.
Oh, because it's multiple of 7. So.
Because it's a multiple of 7. So I'll just put an equal mod 7. Okay. Now, what I want to do is, what times 3 is equal to 1 mod 7? 5 times 3 is 15. Right, so does everybody agree that 5 times 3 is 1 mod 7? So if I multiply 5x is going to go into 15 plus 5 times d0. They'll be the same mod 7. But 15 is the same as 1 mod 7. So 5x is the same as 1 times that beginning digit. Now 5 is the same as 7 minus 2. Minus 2 d0. And there's your rule.
There it is. Everything up to D1 minus twice D0.
Minus twice. And now here's the thing. 5 times x, well, 7 doesn't go into 5. So if I want to know, is my number x a multiple of 7? If this thing is a multiple of 7, since 5 is not a multiple of 7, x must be a multiple of 7.
That's awesome.
What you could do as an exercise homework problem is, what if you wanted to remove the last 2 digits? What would be the new rule of divisibility? Because here you've got that big number to look at. So maybe you want to split it a little bit more evenly.
You mean, is it a different rule of divisibility?
It would be a different, well, you want to find what would be the rule of divisibility if you pull off d1, d0. So, but this is always, when you teach us, ask people to generalize. So when I was visiting my daughter's 4th grade class, I saw the rule for divisibility of 7 on the board. I go, really? I never got divisibility by 7. And so I then proved to them why this worked. So this is a nice place to end the morning. But when you have a large number, you can just keep reiterating this method. And every time you iterate it, your number is going to get smaller and smaller and smaller. So if you have n digits, you shouldn't have to do this more than n times. So it's going to run again in logarithmic time relative to the size of your number. Okay. This will be a good place to stop.